This presentation covers short-range behavior for Team Saturn. The objective for the ASAP robot to complete was to follow a manually controlled robot with a mounted orange pylon within plus or minus 15 degrees without crashing into it. Strategy to accomplish the objective involved capturing the target via vision, locating the target center of mass by paying only attention to the x-axis since y-axis data would not be relevant, determining the position of the target relative to Saturn's field of view using a K-structure dependent on the pixel value of the center of mass, and powering the motors based on the position within the K-structure. The vision processing sequence we used relied on RGB values and a smoothing median filter. The color threshold used the RGB color model. We attempted using the HSL color model but obtained a higher success rate with the former. The histogram used to filter out ranges was set to linear to improve the readability of the information. We found that the red range was the most important since orange is in large part composed of red. The smoothing median filter was instrumental in filtering out small particles, which would lead to errors in locating the orange pylon. However, increasing the filter size values limits the effective distance since the orange pylon would effectively become a small particle to be filtered out at a farther distance sooner. The particle data is sent into an array, and the only values of interest to the code determining the behavior are the x-axis center of mass in pixels and the range in centimeters from the IR sensor. A key portion of the behavior was setting the default behavior to be the previous speed values should the orange pylon fall out of sight. This setting prevented any pulsing and jittering behavior we experienced early on. That behavior was apparent since we had such a low frame per second that the target would often leave line of sight while still operating on the previous frame's data. Saturn's turning behavior is determined by the pixel value of the center of mass for the x-axis. The turning behavior operates partially on constant values and on linear functions. If the center of mass is on the edge of Saturn's field of view, Saturn would make a hard turn versus the target being closer to the center on Saturn's field of view. Saturn would make a gentler turn, almost appearing straight. During the demonstration of Saturn's performing short-range behavior, it was able to accomplish the objectives of facing the target within plus or minus 15 degrees, stopping without crashing, and resuming following behavior. Saturn could only achieve a frame rate of 2 frames per second, which greatly limited its performance. The captured distance was approximately 10 feet, which was partially limited by the smoothing median filter. Saturn could usually stop within 20 centimeters of the target. At times, the infrared sensor and the target's frame would not be aligned, leading to stopping issues. To help achieve the performance obtained, we reduced the video capture resolution to save on processing power. We also disabled unused modules like GPS, compass, and accelerometer, using disabled structures to save on processing power. Finally, we set the stopping value higher to account for delay in frames. There were multiple obstacles in achieving our objective. The lighting at first seemed to be the largest issue, but with several tuning sessions in a shadowy location, it was not too much of a problem. The actual greatest inhibitor of Saturn's demonstration was the processing power, to be able to provide more frames. This would give Saturn more reliable and up-to-date information during real time. The narrow field of view of the camera and infrared sensor also were issues when the target will leave Saturn's line of sight. Thank you for watching the short-range behavior presentation from Team Saturn.